In this series, we look at the different systems that impact on the climate of Earth. Through 5 episodes, we take you from the edges of the solar system to deep within our own Earth, analysing how our climate emerged and developed. We will also look into the current global climate situation and what the future holds for Earth. Welcome to Climate. You may think that the effect that the biosphere has on the climate is minimal. It's only a bunch of plants and animals, right? How can they affect the global climate? Well, the biosphere is the summation of all life on Earth. Plants, animals, insects, fungi. If it's alive, it's part of the biosphere. And if it's part of the biosphere, it has effect on the climate. Not only is the climate sensitive to the changes in the biosphere is sensitive to changes in the climate. In this way, small changes can make a big difference. The Earth has existed much longer than life has. After the formation of the Earth, 4.6 billion years ago, it took around 800 million years for life to emerge. At the start, life evolved slowly. Simple single-celled organisms took 2.8 billion years to evolve into multicellular organisms, and a further 500 million years before the first animals and plants emerged. This dawning of life, however, changed the climate dramatically. Prior to the biosphere existing, Earth was dry and arid, volcanism was rife, and the chemical composition of the atmosphere was much different. The emergence of life had a large effect on the atmosphere, reducing levels of atmospheric carbon dioxide and boosting levels of atmospheric oxygen. Gas exchange between the biosphere and the atmosphere is a key interface in paleoclimatology and has aided in the sculpting of the climate into what it is today.
The first cells to exhibit photosynthesis emerged 3.4 billion years ago. Photosynthesis uses light to combine carbon dioxide and water to produce glucose and oxygen. Overall, the gaseous exchange involved in photosynthesis extracts carbon dioxide from the atmosphere and releases oxygen. Plants might not look like they're doing much, but each year global photosynthesis captures 6 times more energy than has ever been used by the totality of human civilization. Photosynthesis is not the only method of gas exchange used at the biosphere-atmosphere interface. Respiration, the energy-producing process for all plants and animals, including humans, involves the use of oxygen to metabolize glucose, producing carbon dioxide as a byproduct. The overall gas exchange in respiration involves extracting oxygen from the atmosphere and releasing carbon dioxide, the opposite of photosynthesis. The two processes combine to produce a delicate balance of atmospheric gases. This balance is known as a positive feedback loop. As photosynthesis increases, more oxygen is released into the atmosphere, which subsequently increases the rate of respiration, which increases the amount of carbon dioxide released into the atmosphere, which further increases the rate of photosynthesis until other limiting factors end the loop. As atmospheric carbon dioxide levels increase, mean global temperatures increase. This allows areas closer to the poles to be habitable for photosynthesizing plants. This increase in terrestrial plant numbers decreases the amount of carbon dioxide in the atmosphere due to an increase in photosynthesis. This is an example of a negative feedback loop, one with a self-regulating effect. Along with carbon dioxide and oxygen, methane is released by many animals and bacteria. Carbon dioxide and methane are both greenhouse gases. These gases trap heat from the sun in the atmosphere, increasing the temperature on Earth. Although each individual member of the biosphere affects the climate minimally, the summation of the organisms impact the climate dramatically and have done so throughout history. But how can we deduce the extent to which this has happened? And how have we established the time frame of the biosphere? Simon took a look at the biological proxies and what they can tell us about the history of climate change.
Climate proxies are used to establish what the climate was like at a specific point in time. They range from ancient gas locked in Antarctic ice to the chemical composition of fossilised matter. Analysis of these proxies enables scientists to Due to the delicate nature of the interface between the biosphere and the climate, any changes to the climate chemically impact on organisms within the biosphere. These changes can induce physical alterations which, if preserved, can be viewed and dated today. Fossilised biological material can accurately reflect climates of the past. For example, by analysing the magnesium and calcium content of these shells, the level of atmospheric carbon dioxide present in the atmosphere when the shell was formed can be deduced.
Back to the present day, and the biosphere is as crucial as ever. Human-induced climate change is most commonly associated with greenhouse gases being emitted from factories and cars, but human manipulation of the biosphere throughout the Holocene has had a big impact. Deforestation and forest fires both remove photosynthesizing trees and plants from the biosphere, while simultaneously releasing carbon dioxide into the atmosphere. Human-induced extinctions have accounted for the loss of thousands of species from the biosphere, each of which played its individual role in the balance within the system. In this series we have travelled through millions of years, from outer space, where we saw how the Earth's orbit and tilt changed to force the climate into greenhouse or icehouse states, down into the atmosphere, looking at greenhouse gases and the effect carbon dioxide release had on the paleoclimate. Across the ice caps, explaining the feedback effects of low albedo and seeing the evidence that proves they once helped to develop a completely frozen Earth. Deep into the oceans, studying how the diversions of ocean currents in the past drove the warming and cooling of continents. Inside the Earth, observing how plate tectonics drive volcanism and rock weathering and the consequences for the carbon cycle, and ending back on land, discussing the effects life has had and will have on the global climate. Though each system appears separate, they all interact. Their feedback effects combine to develop very different climates across time. This makes the whole climate system very delicate, susceptible to the smallest of changes, proven by proxies of previous rapid climate changes. It is up to us to ensure that humans do not shape the future, allowing our fragile planet to follow its natural path. We hope this series has been helpful, and thanks for watching.